Assalamu alaikum. This is AS Chemistry, and today we're going to be doing atom economy. We're going to see what would be considered a high atom economy and a low atom economy, and then we're going to solve a question to see how you can solve for atom economy in exam questions using its formula. So let's begin. So if you're someone who's completely new to this concept, then this example is for you. Okay, so listen closely. Let's say that imagine that you're baking a cake. Okay, so you mix flour, egg, sugar, butter. Okay, all of these are your ingredients, but I can also call them your reactants. So your eggs, sugar, flour, butter is your reactants. Okay, and your cake is going to be your product. Okay, so if all of your reactants, the eggs, sugar, butter, all of your reactants turn into a cake that you can eat, then that's 100% atom economy there. Okay, if all of your reactants convert into the cake that you can eat, that's 100% atom economy there. But if, let's say, you leave the cake in the oven for a bit too long and parts of it burn, so let's say the bottom of the cake is burnt now, you're going to have to scrape the burnt bottom and throw that away. Or let's say that there are a lot of crumbs, okay, from the cake that you make, that you're going to throw away. So you throw away some of the crumbs, let's say. So you lost some of those ingredients. Some of those ingredients, the flour, sugar, egg, butter, are wasted because you're throwing those crumbs away, right? So that's going to give you a lower atom economy. If the ingredients turn into a cake that you can eat, that's 100% atom economy. But if the ingredients turn into a cake, parts of which that you are going to have to throw away because of whatever reasons, your ingredients would be wasted, and that's going to give you a lower atom economy. Does that make sense? So in this example, atom economy would be how much of what you put in actually ends up in the cake you want to eat. Okay, does that make sense? Now, to give you another example, let's say you're going out and you give your sister all of the ingredients that she's going to need to bake a cake, and you tell her that you need a big pound cake. Okay, you need a pound cake. You don't need any other thing. You don't want her to be experimenting with these ingredients. You give her the ingredients and you tell her, I want a pound cake from this. But when you come back, you see that she's used those ingredients to make a pound cake, which is smaller. Okay, and she's also made a few cupcakes, which you didn't ask for. Okay, that wasn't your desired product. Your desired product was the pound cake. Okay, but now you have two products, one of which is what you wanted and the other one is the byproduct. Okay, so some of your reactants or some of your ingredients are wasted in the byproduct, which is the cupcakes. You didn't want the cupcakes, you wanted the pound cake. Okay, so if you have two products being made, one of which is your desired product, the other one is your is a byproduct, then you're going to have a low atom economy compared to if you asked your sister to make a cake, you gave her everything and she made a simple pound cake for you, and no cupcakes. Okay, that's a higher atom economy compared to when she made cupcakes with the pound cake. Okay, does that make sense? Okay, hopefully it does. Now, when we're talking about atom economy in chemistry, we're talking about how much of the reactant atoms, if I can write this here for you. Okay, how much of the reactant atoms end up as the desired product. I have a definition written for you here, this one, which is proportion of atom economy is the proportion of reactant atoms that become part of the desired product rather than becoming byproducts. Okay, so in simple terms, put simply, this is what atom economy is: how much of the reactant atoms end up as the desired product. So now if we see an example for high atom economy, when would we say, well, the atom economy of this reaction was high? So let's take an example. Let's take an example of formation of water. Okay, so you have hydrogen with half oxygen, and that gives you water. Now I'm gonna say that this reaction here has a high atom economy because there are no waste products. All hydrogen atoms and all oxygen, so all hydrogen and oxygen end up as one product, one single product, which is water. So what is high atom economy? High atom economy is when you have most atoms of the reactants. Okay, so most atoms end up in the useful product. Okay, on the flip side though, low atom economy is when lots of atoms end up in the waste product. Okay, so if lots of atoms of the reactants, of course, end up in the waste products or byproducts. Okay, so if I give you an example of low atom economy, consider this example. So where you have cyclohexane, okay, and that whatever process occurs here, okay, and that gives you C2H4 plus C4H8. Okay, this is ethene, this is butene. Okay, so now your desired product, let's say your desired product was ethene, you wanted ethene, okay, but you're also ending up with butene. Okay, so lots of atoms from here. Okay, so it's like this, atoms from the reactants are going into two products, so they're being wasted. If you look here, the reactant atoms are all going to the same product. Okay, so this is low atom economy and this is a case of high atom economy. Now let's solve a question. So we have ethanol can be produced by fermenting glucose, C6H12O6, in this reaction. Calculate the percentage atom economy for this reaction. All right, atom economy has this formula. Okay, atom economy is equal to molecular mass of the desired product. Okay, divided by sum of molecular, so it's going to be all of the reactants, so sum of molecular masses of all the reactants. Okay, I'm not writing products here, I'm writing sum of the molecular masses of all the reactants, not products. Okay, and since it says calculate percentage atom economy, you're gonna have to multiply this by 100. All right, so let's solve the question. The first thing that we need to do here is to calculate the total mass, so total mass of the reactants. So the total mass of the reactants, in reactants we only have glucose, so use your periodic table for this. So 12 times 6 plus 1 times 12. Okay, plus 16 times 6. And that's going to give you your total mass of the reactants, which is going to be 180 grams. Okay, and then the second step is going to be to calculate the molecular mass of the desired product. And the desired product in this case is ethanol. We're talking about ethanol, right? Of the desired product, which is in this case ethanol. So if you calculate the mass of ethanol, you get 12 times 2. I'm only doing it for, I know some of you may already know how to calculate mass and all, but there are some people who are new to this, completely new to this concept, so it's for them. If you know how to do this, you can skip ahead in the video. So 12 times 2, because one carbon is 12, and then times 5 plus 16 for the oxygen, and then for the lost hydrogen, 1. Okay, this is 1.0. All of this together is going to give you 92. Okay, now if you go back in the equation and see the desired product, which is this one, it has 2 moles being made. Okay, so you have 2 moles of the desired product being made. So you're going to have to multiply the mass of the product, which you just calculated, which is 92. In fact, this is not going to give you 92. This is going to give you 46. Okay, so you go back in the equation, you see, well, you have 2 of the ethanol molecules being made, so you're going to have to double this. Okay, so you see in the equation how much of the desired product is being made. You also look at the coefficient right next to the desired product. Okay, so we have 2 of ethanol molecules being made. This is for 1, right? So you times that by 2, and that's going to give you 92. Okay, then you put all of this, the calculated this part and this part, in the formula. So the formula says the molecular mass of the desired product goes up. So 92. Okay, 92 divided by 180 times 100, and that's going to give you 51.1%. Okay, so that's your atom economy here. It's almost 50% atom economy, and this is it.